Thank you. Our next speaker is Michael Moortgat. He's going to tell us about a dependency-enhanced type logic. Take it away.
Okay, thank you for having me as a speaker. I hope you won't regret it, actually, because this talk is going to be entirely devoid of quantum techniques. But I'm sure by the end of the week, I will have learned about many opportunities to actually employ them. Let me see. So this is the idea. As the previous talk, I'm going to assume as a background Lambek's original syntactic calculus, but now generalized for arities. So that means that in addition to the usual tensor with its two slashes as adjoints, there also will be a unary residuated pair of operators, the diamond and the box operators. And if you have listened to work emanating from Utrecht University, you will have seen that the main use of these operators actually has been similar to the use of the exponential in linear logic, namely to have structural extensions that allow you to formulate controlled forms of restructuring and reordering on top of the pure residuation logic that Lambek defined. So the bang, the linear logic bang here would actually be a defined operator, the composition of the diamond and the box operators, which defines an interior operator on the type system. Now in this talk, I'm going to look at a different use of modalities, namely as dependency features that are going to code for grammatical roles, subject, object, adverb, etc., etc. And the result of that will be a type logic that you could call multidimensional, in the sense that it simultaneously induces a dependency structure and a function argument structure on the linguistic material. As usual, this talk owes a lot to the Utrecht, the gang of four, and they will make an appearance in the slides at the appropriate places. Now, the background. So some of you may wonder, dependency-enhanced types, why this Lambek calculus compared to pre-groups is already so complicated? Why should we make it even more elaborate? The motivating background is actually two nasty problems of natural language processing, two forms of ambiguity issues that you actually find everywhere. And I think Stefano this morning or earlier today mentioned them already. One of them is lexical ambiguity. So think of cases like time flies like an arrow, or Groucho Marx, I shot the elephant in my pajamas. You have words here, flies or like, which would be associated with different categories, right? It could be a verb, flies, it could be a plural noun, etc., etc. I shot the elephant in my pajamas, the modifier here in my pajamas, it could modify the elephant, or it could be an adverbial modifier of the verb. It's clear what Groucho Marx will think here. He continues, how it came into my pajamas, I really don't know. And if you have ordinary categories, say part of speech categories, which are unstructured, then already the problem of lexical ambiguity is already there. But if you go to a typed system, like Lambek calculus, the types are much more informative, which is a good thing, because in these systems, as they say, you almost have done the parsing as soon as you have identified the correct types. On the other hand, with these detailed types, you will have a greater amount of lexical ambiguity. Then the other problem is derivational ambiguity. So here, if you want to think of an example, would be something like, why do you think the prisoners escaped? Which could be a question either about the reason for your thinking, or it could be a question about the reason for the prisoners to have escaped, for example, because they didn't like the prison food or whatever. So in order to address these issues, we move to this multidimensional Lambek calculus. And the outline of the talk is going to be pretty simple. First, I will look theoretically at the extended system, and I will try to place it into the wider context of type influence from structured input. Then we move to the practice, and we are going to see how this machinery can be put to use in type inference and parsing for Dutch, a language which some people have called a non-natural language. This goes back mainly to the thesis work of Konstantinos Kokkalidis. And then finally, I close with some to-dos and some problems that are still open. Okay, type inference. There's a classic reference here, which is the article by Buskowski and Penn, 30 years old now. Categorical grammar is determined from linguistic data by unification. And the idea here is for this linguistic data that the data would actually be structured. It's not simply flat strings, but it's a structured input. And the structures take the form of binary trees, full binary trees with words at the leaves. And then for the internal nodes, they have a distinguished daughter, a preferred daughter. So in the notation here, I've used these triangles to actually point to the distinguished daughter. And an example would be, you know, idea sleep, green idea sleep furiously, etc., where you see for each internal node which of the daughters is going to be the distinguished one. Now the algorithm to extract types from these structures goes like this. Your input is a goal type, so you fix some goal type. Your input is a set of these structures with distinguished daughters. A set or an infinite sequence, actually, in the context of identification in the limit type of learning. The output is going to be a lexicon, which is assigning the input words one or more types. And the way the inference then works is, well, you first label the root of your inputs with a goal type. Then you label each of the non-distinguished nodes with a fresh variable. So that's the nodes which the triangles point away from. Step 3, the only nodes that don't have a label at that point are the distinguished nodes. And you type them in such a way that for each of the subtrees now you have the label for the root, the C in this case here, and you have the label for the non-distinguished daughter. So you can simply, by residuation, if you wish, fill in then the missing label for the distinguished daughter, which will be A under C or C over B, depending on whether it's the left or the right factor of a product. Once you have done that, you can collect the different types that you find for each word. And then the final crucial step is that you are going to unify the type set for each word as far as possible. And the unifying substitutions that you find are going to be performed globally over the whole lexicon. That's the very simple algorithm. Here is our colorless green ideas. If we run the algorithm on the data set here, you'll see the lexicon that I'm displaying here. In general, what you see is that apart from this fixed goal type, the sentence type here, which was labeling the root of our structures, there is only one variable, extra variable that is being used, the x here, which if you wish you could read as noun or noun phrase or whatever. And in general, then the algorithm it works with the number of distinct variables, which is going to be exactly the cardinality of your set of atoms minus one for this goal form, for this goal type. Okay, that's function argument learning in the Buskowski-Penn sense. But now, in order to alert you to the problem, these structured data, there is another obvious interpretation that you could think of, namely prosody. So in prosody, if you look at our opposition between distinguished and non-distinguished daughter, in prosodic sense, this would code for relative prominence, actually. So it would be a distinction between a subtree which is having a strong and weak element, or a weak and a strong element. And then depending on the language that you are talking about, the realization of that prominence could be in terms of pitch accent, as we have it in say, English, or it could be a tone melody in a tone language, or whatever. So here what you can do in order to cash out on that prosodic model is assign a weight to the leaves of your structured data. The weight takes the form of a bit string. which you obtain by actually following the path from a leaf to the root, reading the strong nodes that you pass as 0 and the weak nodes as 1. And then the binary number that you find is going to express the relative degree of subordination. So that means that the leaf which gets the lowest value in binary is going to be the element that is prosodically the most probable. Now, let's give an illustration here. The illustration is from a language which is unfortunately not being spoken anymore. Vano. This was spoken on 2 tiny islands of the Solomon Island group. Last speaker died in 2008. But fortunately, there is an epic, the myth of origin, the Batatuku, which is preserved on palm leaves. That's the paper that they are using there. And because this is a sacred text, it's very important that when it is recited that the recitation is proper. So that means that the script that they are using uses a kind of system of diacritics in order to guarantee this proper pronunciation. So here is the I'm sorry, the palm leaf original. Now, if we look at our structured data here, for example, this particular sentence, which means like Billy makes Kaba capsize or something. It's all about a battle, sea battle between these canoe people. The way it would be pronounced, if we read the prosodic weights in the way indicated by the algorithm, would be rendered as something like Billy Kaba Tubiko, with the causative morpheme in primary stress position. Okay. Now the question that arises here, function argument structure and the prosodic structures that I'm just discussing, is what's the alignment between these two pieces of information? And if you just think about English prosody, for example, it's going to be clear that the function argument structure and prosodic structure, in general, are not going to be aligned. So what you would need actually is a type logic which is multidimensional in the sense that it can simultaneously give proper weight to these two forms of information. Sorry for the. Now, this brings us to the case that I actually want to discuss with you: function argument structure versus dependency structure. Where for the dependency structure, actually, there's two oppositions that play a role here. The opposition between a head and the complements that it selects. For example, in the verbal domain, subjects, indirect objects, etc., etc. In the nominal domain, maybe objects of prepositions, blah, blah, blah. This on the one hand, and on the other hand, the opposition between an adjunct, a modifier, and a head. For example, manner, time adverbials in the verbal domain, adjectives, numerals, determiners in the nominal domain. And there's a tension between these two. Take, for example, the determiners. Semantically, they would be characteristic functions of relations between the semantic spaces that interpret the noun they combine with and the verb phrase they combine with. But morphologically, the determiner is going to be dependent on the head noun in the sense that it will inherit case information, number information, etc. Now, this problem has been discussed before in categorical literature, actually, in a very old paper that was never published, which I did with Glyn Morrill. And our idea there was, why don't we take the Lambic tensor and split it into a left-headed versus a right-headed version? So the left-headed version has, the distinguished daughter, if you wish, on the left, and the right-headed version on the right. Then, if you play the residuation game, then you have the two residuals for each of these products, of these tensors. And you can now actually make a distinction between functors which are heads, which would be the C over B, but for the left-headed product, versus A under C for the right-headed product, and similarly functors which are dependents, which are non-heads, which is the remaining two of the four. Okay, so that's all nice and well. And only what we can do now is we can look at these two headed products, and we can see whether we can actually deconstruct them and view them as compositions of the regular tensor operation with the modal marking of the dependent, because that's the element that's going to be the semantically significant one, actually. So once you have set the definition for the tensors, the two-headed tensors, the translation for the slashes pardon, is going to follow directly from the residuation laws, where you have to recall that for the diamond and the box operations, the residuation pattern works as indicated here. So let's see what we get. What we want to do to actually put this into use in practice is a multimodal generalization, where instead of just one diamond and a box, we consider families of them, families which are indexed by dependency labels, either for the complements or for the adjuncts. Okay, good. So colorless green ideas. If we want to do a type inference now from structured input, the structured input that we need is actually going to have a four-way marking for the internal nodes. I'm using these compass needles here. The black tip is where they point. So for the north east and the northwest compass, this is going to be used to actually infer the head functors, and for the southeast and the southwest compasses, you are going to infer the dependent functors. And you see that the head functors, they have the diamond marking on the argument, on the complement which is selected, whereas the modifiers, the adjuncts, have as a primary operator, have the box operator, which has to be unlocked before actually the implication in these types can be used. So now with this four-way marking, the structured data for our colorless green ideas is as indicated, and lexicon that would result here gives you now the following types, where concretely, say, the green would be a noun modifier, a nominal modifier. The sleep would be an intransitive verb selecting for a subject. The furiously will be an adverbial modifier, which is a function taking an intransitive verb into a new intransitive verb, etc. So that's the theoretical background on the type inference business. Now, in practice, there's a couple of papers that you can look at. There is an LREC paper, which is called ETL, and this is a resource of automatically extracted typological derivations using this type system for Dutch. This is talking about real data, like something like, I think, 65,000 sentences for 1 million words or so. And if you do the type extraction here, you come to something like 5,500 unique types, built out of 31 atomic types and 26 dependency relations. So the code and the data itself is available on GitHub. And if you want to play with them and try out your quantum techniques, as we heard in Stefano's talk or the other Konstantino's talk, feel free to do so. The second paper is about using this kind of type system to then develop a neural machine learning version of proofnet construction. And I will briefly illustrate the two ideas. So the structured data that we actually work with here is the Dutch tree bank, which is called LASSI. And the kind of data that you find there is it's syntactic trees with syntactic categories in red here at the nodes. So part of speech categories at the pre-terminals and then phrasal categories at the internal nodes. And the links, the arches are decorated with dependency labels. So swallows twitter in the skies, with thanks to John Keats here, would be the translation of some Dutch example, where swallows is the subject, twitter is the head of the whole main clause, and then there is an adverbial modifier, etc., etc. So if you do the type extraction that we were just discussing, then you get the types at the bottom of the slide here. And now, when you have these types, in order to construe a parse for them, what we do is actually, first of all, is you build the word modules, which is nothing but the formula decomposition tree, if you wish. The directionality here is significant in the sense that you have the bottom and you have the top here. So there's a flow of information from top to bottom. And the whole idea of constructing a proof net now is actually to connect the tentacles with opposite polarity, input versus output polarity, which is in this particular case is going to give us the following links. Now, for correctness, you have to check that the resulting data structure is actually a tree, which is in this case is trivial. It wouldn't be trivial if there would be higher order types around here, but I'm not going to discuss them given the time. So then finally, from a proof net, you can, by the usual Curry-Howard correspondence, you can extract a linear lambda term. And the important point here about this linear lambda term is that there is the image, if you wish, or the reflection of the diamond introduction steps and the box elimination steps, which, when you think of the distributional interpretation here, is going to be operations that work on the distributional meaning of swallows or whatever, in order to modify it by this subject gap operator here, and then give it for a contraction to the intransitive verb tweet, etc. So here is dependency structure, which derivation, in natural deduction style, which I grayed out because I think everybody here will hate symbolic computations. And the important point is that from this derivation, you will be able to induce the dependency structure by just taking within each dependency domain outgoing arcs from the head, Twitter in this particular case, to the heads of the dependents. Okay, so that's the double projection of function argument structure and dependency structure. Now, the to-do list, what we have to do in the first place is to rethink constituency, actually. Because the standard picture that I started from at the beginning has this, this doubly residuated tensor and diamond system, plus structural extensions for controlled semi-associativity or semi-commutativities. And they have been used, for example, to model extraction. Here is the type for a Dutch relative pronoun, which says, well, this hypothesis here is going to have to find its place somewhere in the subordinate clause in order to semantically interpret it. What you have to recall here is that Dutch is a verb final language where all the complements are actually preceding the verb, which is the cause for this ambiguity. But now with the dependency annotation, what you actually see is that our notion of constituent can be equated with a dependency domain, and that creates opportunity. So one of the opportunities is that you could say, well, within this dependency domain, why would we assume that the tensor is non-associative? We could as well assume it is associative, or even in a more radical setting, you could assume that it is associative commutative. So dropping the non-associativity means that your constituent structure is going to be flat, which is a good thing, in order to reduce lexical type ambiguity. If you further relax the linear order, then it's possible for a head and its complements to be realized in different orders. And this is exactly what you find in a language with rather free word orders, such as Dutch, where instead of having the subject-verb adverbial order, you could as well have the adverbial-verb subject order. And these will now all be derived from one and the same type, rather than generating different types for the different linear orders. So that's good. Reducing derivation ambiguity. As I said, so the original analysis for relative pronouns was assuming this bang marking here on the hypothetical resource. This causes ambiguity between subject and object relativization. But with the dependency annotations, now it becomes actually possible to distinguish a subject extraction relative pronoun versus a direct object extraction relative pronoun. That's good. The main thing to do is actually to combine the dependency marking with non-local forms of extraction or dependency in general, which in this case would involve structural postulates that actually license you to cross the dependency boundaries in order to enter a deeper dependency domain. And the fascinating thing here is that you could actually do that by assuming that there is say, a boundary strength ordering on these dependency relations, which allows you for certain dependencies to actually penetrate other domains, whereas for other dependency relations, the domains will actually be complete islands that cannot be penetrated. So here is my end of talk thing, and I think I used up the time.
Thank you, Michael. Yeah, I think we've possibly just run out of time now, but anybody, I encourage everyone to continue the discussion in the Slack channel.
Okay.
Okay. Thank you again, Michael.
Thank you.